So suppose that this is a very important distribution, the beta, right? Usually when you're trying to analyze some probability questions, you do not know a priori what's the probability of the event you're studying. So for example, you want to know how prevalent a particular disease is in the population, right? That is a ratio. Let's say how many people are sick divided by total population. So that can be thought of as a probability, right? What's the probability that a randomly selected person is sick? Usually you do not know that probability ahead of time. You don't have the ability to look at the entire population. So you can think similarly that suppose you have a coin, and the coin can land on heads with some probability p, but that probability is not known to us. So our goal is to infer the value by conducting n tosses of the coin, independent tosses, and seeing how many of those tosses come out heads. And given that information, we hope to estimate what's the actual probability for that coin to land on heads. So we know that p is between 0 and 1. And if we know nothing about any coins, any distribution of coins, it's natural to assume that this probability is equally likely to be anywhere between 0 and 1. So it's natural to assume that the probability that coin lands heads is uniformly distributed. Make sense? Okay, so by default, if I am seeing a new situation, I do not make any predictions. To me, every every probability is equally likely because I don't know any better. And if you read a little bit of those notes, you realize that the uniform random variable is just a particular instance of the beta distribution. So beta distribution is just a way to mold a curve, a density curve over the interval 0, 1. So it can take many complicated shapes. Right? And one of those shapes could be as simple as just a horizontal line y equals 1. In other words, the uniform distribution is already contained as a sub possibility, as a member of this bigger beta family. Okay, beta family with AB. So it's even more natural to assume that the actual distribution, the actual density function for the probability p, the probability that coin lands heads, is some parameter w, which is beta AB. Okay, Eli, you missed that class. Do you need me to show you again what's beta AB? I suppose. So beta AB, we talked about it before. It's just it looks like this. This is the density function. So it's x to the a minus 1, y minus x, b minus 1, where when you integrate it from 0 to 1, you multiply by a corrective constant to make sure that the area, the total area, equals 1. So that corrective constant is just the integral from 0, 1 of this expression. Okay. We spoke about how to figure out what's the integral by combinatorial argument. It's presented over here. If, of course, you either you look into my notes or after class, I can again re-explain this.
So what's the normalization factor?
It's the normalization factor. Beautifully said, Jeremy. Right? So it's the normalization factor. Okay, and there were quite interesting calculations. I think some calculations that I think you particularly would have enjoyed because you like physics, and it seems to. Somehow it's marks of the same things that happen when you solve a physics problem. So yes, so again, we want to figure out this probability, and again, we by default, when you don't know anything about the phenomenon, you assume that the density function is y equals 1. In other words, uniformly distributed. Or if you want to, you can therefore assume with even greater generality that the distribution is some beta distribution, because that contains more distributions than just the uniform random variable. Okay, so in my notes, I don't want to use p again because it might be confusing. So I call the w the random variable that has this beta distribution. And that's the probability in German, Wahrscheinlichkeit. That's why it's W. It's the probability that you know, their probability for this coin, right? It's a random variable. You cannot predict P for certain because I cannot flip the coin infinitely many times, but I can give a range of predictions. In other words, I can if I have many experiments, I can predict the probability fairly accurately. If I do enough many experiments, I can predict it accurately to within 1 decimal or 2 decimals or 3 decimals. You can predict it. Yes. So that's a possibility there. So then the question is, how do I update W given the information that let's say X is the number of successive heads, so the number of heads that I obtained. Okay, so I flip the coin, let's say 100 times, and 30 of them came out heads. What does it tell me about the distribution? How do I upgrade it? Okay, so in other words, so the original density function for W is given by this beta distribution. And what we want to calculate is what you call marginal density function. We haven't spoken about marginal densities, but I think you can understand the argument well enough this way, right? What we're interested in is that this is the function G, where G of P will give you the density, so that's my notation, restricted to the situation where X came out to be K. In other words, where I had K, out of the n tosses of the coin came out heads. So stop me, guys. You're all quiet. There's uncanny lack of noise or texting. So stop me, or if I have to re-explain something, please. So how do I figure out this function G? By default, the function G should satisfy the following, right? G is just G at P is just the height of a rectangular column, of a thin rectangular column, such that G times dP, where dP refers to a very, very small difference in probabilities, will be an estimation of the probability that near P, that the probability actually is near P. Okay, so the easiest way to calculate it, to calculate G, you can do it using integration. Just you then have to use chain rule and a bunch of or quotient or a bunch of ugly calculations. It's easier to just realize that by the virtue of, or by the property that G has, that it's a probability density function. We are interested in essentially if I ask what's the probability that the random variable W is between P and P plus dP, given that X came out to be K, that is the number of heads that we saw in the experiment was K heads out of N. So that would be GP dP. Okay, so then I continue making this calculation. So GP dP is equal to this probability, which upon using Bayes' formula, you know, I change conditions. So I have that this is equal to the probability that X will equal K, given that W is between P and P plus dP. In other words, essentially saying that given that W equals to this probability, how likely are we to see this many heads? Times the probability that W is between P and P plus dP, that is the original estimation, right? Divided by the probability that X equals to K. So let's try to fill in those factors, okay? So first part, the probability, the denominator, what's the probability that I actually get K heads? That would be just conditioning upon all the values that P can be. So if P equals to 1/2, X equal to K is just the binomial distribution with probability half. If P equals to 1/3, that's the binomial distribution where the parameter is 1/3. So X equal to K, once I know the probability for tossing the coin, is just a particular binomial distribution, right? And so I can use conditioning, and just in this case, I have many conditions, right? So this integral just means sum. So remember how you considered conditioning. If you have 3 events, event A, B, and C, then you would condition P equals, so X equal to K, given that event A happened, or times the probability event A happened, plus probability X equal to K, given that the event B happened, times the probability that event B happened, plus X equal to K, that's the probability of it, given that C happened, times the probability that C happened. Guys, so are you with me, right? So you understand what I said with A, B, and C. Yes, David said yes. And the others, guys, are you here? Do you have a pulse? Are you with me? All right, so integration is just, you see, when I have many events, what happens? You see, notice this integral just means summation, right? So so the summation of what? Of the particular. So this is the probability x. So the capital X equals to k, given that the probability of coming up heads of the coin is fx dx. Remember, fx dx will represent the probability, my estimated probability that coin comes up heads. And this just means I sum over all of those. So above there, I do an explanation of how you can take a Riemann sum and take the limit of it, and then you get an integral. But this is just a glorified way of saying I have many conditions, not just A, B, C, but I have many of them. And since I add them up, in the limit, it becomes just an integral. So you just get this expression. That's why, Jeremy, I think you would have liked it, since, in physics, you also similarly have integrals coming out in such natural way. Okay, so that would be the probability that x equals to k, given the prior probability, given the prior density function f. Similarly, okay, what about the numerator? How do I calculate probability that x is k, given that w is between p and p plus dp? Now, this is almost the same as saying what's the probability that I have k successes, given that probability of success is p, because if it varies just a little bit between p and p plus dp, you might imagine it's essentially p. Okay, and in that case, it will be just n choose k, p to the k, 1 minus p to the n minus k. Okay, so I know this part, the denominator, I know the first part of the numerator, and finally I need to know this. And this is nothing more than the original prior probability, the density function, the previous binomial density, sorry, previous beta density function times dp. So you can see now I can cross out dp, and I have a formula for g. G equals to everything you see here except for this dp. Which, if you start ignoring everything, that doesn't matter much. So denominator is just a constant, and choose k is just a constant. So essentially, gp looks like a constant times p to the power of k, 1 minus p to the power of n minus k, times the density function f of p. Yes. And so when I open up this f of p, there is an extra further constant coming out. But in essence, what is f of p? It's p to the a minus 1, y minus p, b minus 1. So when I simplify this, I realize that I have a constant times p to the a plus k minus 1, y minus p, b plus n minus k minus 1. So, and since the integration has to be equal to 1, this ugly looking constant is nothing more than the normalization factor for a new beta distribution. So what happened, notice what I just said. I start with a beta distribution, and once I perform the experiment, I updated my beta distribution. In practice, you might imagine always starting with assuming nothing at all, to be completely impartial to the outcomes. So you start with a horizontal line with a uniform density, and then you update it based on the experiment, and now you already have a bias. You saw, let's say, that coin came up heads many times, so now you think that the density function is lifted up closer to 1, because that's more likely where the probability is residing. Okay, so in essence, what happens is that the new estimate of my probability random variable, given that I had k successes in my experiment, is now a new beta distribution where I just add k, and yes, and to b I add n minus k. So let's see how this is playing out, how this will play out in practice. Okay, so remember I mentioned that that question before, and we spoke about prosecutor's paradox, right? You have to be very careful when you do those calculations to not dismiss data just because it seems that probability is very small. So here is what happens here, right? So we have a coin, it's tossed 1,000 times, and 550 of those tosses come up heads. Estimate the probability that coin lands heads. So you understand the question, right? So I want to know how likely it is that this coin will produce a success. Well, success is landing on the head. Given this information, out of 1,000 tosses, 550 were successes. Would you believe that this coin is fair, or do you not believe that this coin is fair? So here is what we can do. A priori, we know nothing about this coin, so we might as well estimate that probability of heads is some p, and that's an unknown quantity uniformly distributed between 0 and 1. Okay, so again, here I didn't bother calling it W, so I'm just saying that the probability is then a beta random variable with parameters 1 and 1. That just means uniform. Okay, and if we let x be the number of gets, we want to then update this probability given that x equals to 550. Okay, and that means according to what we just derived over there, we just take the A and we add the number of successes, and we take B and we add the number of failures. Okay, and we get the beta distribution with new parameters 551, 451. Okay, so using integration software, and let's say I use my phone very often for that. So I have, I don't think it will be seen too well, but I'll try. So can you see this? Yeah, so there is just an app where I select beta distribution, and I say, well, A in this case equal to 551, beta equals to, or B equals to 451, and I generate the curve, right? You can see what it is. I roughly drew it over here, and I can set up a bound so to make the machine do the integration for me. Or even though it's possible to do this integration, we even learned ways of doing that when the numbers are integers without actually calculating, but basically by a combinatorial argument rather than by using calculus. So do you see this? The distribution seems to, you see, it seems to not be very likely that it's 0.5. It seems to be hovering between over 0.5 and roughly below 0.59. Okay, giving this information. So according to the estimate, the probability that that we are between 0.51 and 0.59 is 0.98. So roughly 98% certain that my true probability for the coin is between those two values. Do you understand what we did, guys? So this gave me an estimate of the true probability. Of course, unless you toss the coin forever, you will never have the exact number for the probability. You can get very close. Okay, so that's the use of that probability. And here is another coin, right? So by the way, the likelihood that the coin is fair, you just you calculate integration, let's say from 0.5 and below, or however you like. It will be, I think, based on this estimation, roughly roughly 6 out of 1,000. Okay, so it's not very likely to be a fair coin. So here is yet another example. So in a city of 12 million inhabitants, it is wished to estimate the number of people that contracted a certain illness. 100 subjects are randomly selected and carefully tested for the illness. Only 2 are found sick. What should be what should be concluded about the prevalence of the disease in the general population? Would you know how to set this problem up, guys? Yes, integrating above, I explained how to possibly do that even without a machine when we're dealing with integers, right? But in general, you can use, like I do on the phone, just you can use an app or some, so to not waste time with it. So how do you set this up for this beta distribution? I would say as follows, right? So initially, I assume by default I know nothing about prevalence, so I might as well. You see, you don't have to worry about being wrong because the probability will update itself, right? It will be the numbers will be changing. It will basically from whatever incorrect assumption you might have initially made, observations will correct your bias. So initially, I might suppose by default that probability is any number between 0 and 1 equally likely, right? Maybe no people are sick, maybe everybody is sick, maybe anything in between, I have no idea. So, so then we have a uniform distribution. Now, our observation tells us that we had 100 trials, we witnessed 2 successes and 98 failures. Success meaning that person is sick, right? So 100 independent trials, 2 successes, 98 failures. That means that I, based on the calculations above, have to update my beta distribution by adding 2. So in other words, it's no longer 1, 1, it's 1 plus 2, and 1 plus 98. So it's now beta with parameters 3 and 99, okay? And when I press those betas into my machine, or I can do it by hand possibly, all right? If you go up, you can see how you can, without calculus, do integration in the event those numbers are integers. Right? When they're not integers, it can be much more complicated. So I plug in those numbers. This generates a lopsided beta as we expected, right? We don't think that it's very likely that 100% of the population is sick. We think it's more likely that it's closer to 0 than to 1, right? So we have this lopsided distribution here. And then we look at the numbers, right? It's very unlikely that let's say even 12% are sick, right? But 10%, well, not very likely, right, as well. But then it begins to be more and more likely as we move closer to 0. And then I might say that the following. So between 1% of the population and 10% of the population, the probability that that's the number of sick people is 92, roughly 92%. Okay, so that gives me an estimate on the probability. Like if I have a bigger sample, I will have a better estimate. Okay? I can be more certain about the actual rate. So here I am fairly certain it's between 1% to 10% of the population that have contracted the illness. Good. And then one more question regarding that, very similar. So suppose that we're testing a new medication against migraine, and we selected N participants that suffer from this disease. Let's say, and then we are going to administer this medication. Good. We're going to administer this medication to each of those participants and see if there is any effect of the medicine. So what is your estimated probability that people will feel significantly enough to consider the medicine a success, given no knowledge of how the medicine works? And the that is part A. Okay, so that means that what's the probability that I have exactly K people cured, let's say out of the N individuals, without any prior knowledge of this probability, right? So what is that going to be? So naturally, by default, I would say we don't know what is P because we haven't we don't have any information about this medicine. So assuming no information is given, we are unbiasedly assuming it has prior distribution, which is beta 1, 1 or uniform distribution. And then I calculate what's the probability I get exactly K successes. So that means, what do? It means that I sum over, basically I condition, it's P, it's probability that X equals to K, given that actual probability is P, times the probability that it's P roughly, right? So the probability it's roughly P would be here dP, and the probability of success, given that it's P, will be binomial, so it will be this expression. And therefore, all we do is just integrate this expression. Now, as we saw above, instead of doing this integration, which can be complicated a bit with calculus, you can realize by a combinatorial argument that this probability is simply 1 divided by n plus 1. So that means that if I know nothing about my medicine, I would say that the probability, if it's all sorts of medicine, if the medicine you're given is just uniformly distributed from being not effective at all to being extremely effective, and then the probability of k people feeling better is 1 divided by n plus 1. So in other words, let's say if I have 100 participants, the probability 50 of them will feel better because of this medication, significantly better to consider it medication, is 1 divided by 101. Okay, that's the rate. So that's before we have any information. Now, suppose that we do the testing and find that the drug worked very well, so well for the participants that every single trial was a smashing success, right? So we can consider the medication successful for every single person of the. 1 second. So what are you saying, David? Since it is constant, whatever k is, the probability works is constant. Well, be careful. So probability is when I don't know anything about it, I am assuming the actual number is constant. Yeah. So for each person, let's say we're assuming that each person, if I know the probability of the medication, then it works on everybody the same way. They're identical twins, let's say, right? So it works on every single person. Well, not identical twins. Well, but it works. Basically, it's likely to work on a random person with some probability p in general. And I don't know the probability. Maybe medication is completely not effective, and that means p is equal to 0, or it's extremely effective, and that means p equals to 1. But I don't know what it is initially, and I'm assuming all the values are equally likely for the probability. And in that assumption, if that assumption is true, I do get 1 divided by n plus 1 as the likelihood that k people are cured. But then once I make an observation, that's already, I might know more about this particular drug. I might know if I'm just lucky and I see a very good drug, or I'm not lucky and I see a bad one. So suppose that we found that all the participants that we had felt significantly better. Now we update our probability. See, we had no failures, so we don't update b, but we had n successes. So we have n plus 1. N plus 1 is the first parameter of beta, and 1 is the second parameter of beta. And now that means that my my new estimate is first of all, I need to know the constant for beta. I just integrate over the beta distribution. This is part of the beta distribution, right? We just have this number minus 1, so we have p to the power of n. 1 minus p to the power of 1 minus 1, so there is no need to consider 1 minus p. So it's just the integral of p to the n dp. And that integral is simply 1 over n plus 1. So the correcting constant is 1 over n plus 1. Good? So then the probability that the actual potency of this drug is good enough to cure at 1/2 of the suffering population or more will then be this will be n plus 1 multiplied by the integral from 1/2 to 1 of p to the n, right? Because this p now has this distribution, and that integral simply is once I multiply by n plus 1, we arrive at this nice neat answer, which is 1 minus 1/2 to the n plus 1. So you can now see what's the probability that more than half of the people are cured, right? The bigger the sample space on which this result came around, the smaller is this number, and the closer it is to 100%. Any questions before I move to the next topic? Okay. No. That's wonderful. So I hope you do enjoy this, right? Maybe on the exam we can calculate a few things about the current situation, right? Using beta distribution. All right, so the next topic is exponential distribution. I haven't completely finished writing it all, but for today I think we have plenty. So a continuous random variable has exponential distribution with parameter lambda if this is the density function. Okay, so it has to be, so the random variable here does not take negative numbers. It's 0 or more. You can even eliminate 0 since it's not significant. You can never have, in any continuous distribution, the likelihood of taking one particular number equals 0. So we write this by saying x is an exponential distribution of parameter lambda. And by simple integration, you see that the cumulative distribution is 1 minus e to the minus lambda x. And of course, just like with normal distributions, we have the standard exponential distribution. The simplest formula for it, that's when you have lambda equal to 1. It's just e to the minus x, okay? And if you have this type of distribution, you can simulate every other exponential distribution naturally. You just define, if you want to simulate a distribution with parameter lambda, just define y to equal x divided by lambda. And then you have the probability that y is less than or equal to y. The cumulative distribution that I'm trying to find here is probability that x over lambda is less than or equal to y, or probability that x is less than or equal to lambda y. And that is the integral from 0 to lambda y of e to the minus x, which becomes 1 minus e to the minus lambda y. Differentiating, I get my density function for y, which is the density for exponential with parameter lambda. Okay. Similarly, I can convert in the other direction. If I have an exponential random variable with parameter lambda, if I multiply it by lambda, I generate an exponential random variable with parameter 1. And the calculations are exactly the same. Okay, I just start y less than or equal to x over lambda, I modify it, and I see that I get 1 minus e to the minus x, and therefore the density is e to the minus x. So it's enough, and possibly simplest thing to do is to consider the, let's say, we want to know what's the expected value and variance of the exponential random variable. So I carry out those calculations. So what's the expected value of the random variable here? It's simply the integral from 0 to infinity of x e to the minus x dx. And this can be solved by integration by parts. Yes, and integrating that stuff, you get that the expected value is 1. Now I want to calculate variance, and for that I will calculate the expected value of x squared. So again, I use integration by parts. So I hope you remember that from calculus, integration by parts. And what I arrive at is just at twice the integral from 0 to infinity of x e to the minus x, which is the expected of twice the expected value of x. And since that we already solved before, that's just equal to twice 2 times 1, or 2. So now variance of x is then the expected value of x squared minus the square of the expected value, which is 2 minus 1, which is equal to 1. So both variance and expected value of the standard exponential random variable equals to 1. So this quickly allows us to figure out the same properties for y. What's the expected value of y? So y is simply x divided by lambda, and the expected value is then, we can factor out 1 over lambda, it's just 1 over lambda then. Okay, and the expected value of y squared is simply, I factor out, it's x over lambda squared, so I can factor out 1 over lambda squared, and the expected value of x squared we know equals to 2. We calculated it before, right? So it's 2 times 1 over lambda squared. And then calculating the variance amounts to doing this, and we just get that the answer is 1 over lambda squared. So one very special thing, and I'll have some possibly even personal examples about it. The exponential distribution has a very special property called Memoryless Property. So that says that if you waited for hours or days without success for something to happen, that success isn't any more likely to arrive soon. So in other words, if y represents the, well, I'll actually show this particular example. Hopefully that already is gonna make sense. So suppose that the time it takes me to grade one of your exams is exponentially distributed with a mean of 1, with expected value 1. Okay. So given that you waited for the results 1 month already, what is the probability that it will take another month or longer to grade the test? What do you think? Can you carry out these calculations? Isabella says no. So you understand what? So let's say the time between the moment you submit the exam and the moment you receive it is exponentially distributed with parameter 1. The question is, if you waited 1 month already, given that this already happened, what's the probability you have to wait another month or more? Carry out the calculation, please. Okay, thank you, Ugo. You say, so it's e to the power of -2, you say. But that is, what you calculated, Ugo, is just the probability it will take me more than 2 months to grade the exam. But suppose what happened is that it's already passed, you already know that it took me longer than 1 month. What's the probability it will take me longer than 2 months? And if you could, guys, I would be happy if you turn on the camera so I can look at you. Am I that scary? Not quite. That's the probability it will take me less than 2 months. Ugo. It's this, right? Given that it took me more than a month already to grade it, what's the probability it will take more than 2 months? You mean the 1 minus e to the power of 2, or because the number you wrote here is negative? All right. What about the rest of you guys? Are you trying to solve it? No, Ugo suggested the same thing, Elan, and that's not quite us. Wait a second, did they say longer than? I'm asking for, you see, what you calculated, Elan and Ugo, you calculated the probability that it will take 2 months or more to grade the exam. But I asked you this, I already am working a month already, right? And the exam are still not available. What's the probability then? It's very different. So unconditionally, it will take me e to the power of -2. With probability e to the power of -2, it will take me longer than 2 months. But given that I'm working already a month and haven't returned the exams, what's the probability it will be even longer? All right, so I guess let me help you with that calculation. So again, the time to return your test is exponentially distributed with parameter lambda equal to 1. What do we wish to calculate? We wish to calculate probability that time taken is 2 months or more, given that we already know the time taken is 1 month or more. So that's the same thing as the probability that I just use. It's basically, you see, now we have this expression. That's back to chapter 3, back to conditional probability. So this is the intersection of the events t bigger than 2 and t bigger than 1 divided by the probability that t is bigger than 1. Now, this intersection, you can see that t bigger than 2 is a smaller event than t bigger than 1. So this numerator simply becomes probability t bigger than or equal to 2 divided by probability t bigger than or equal to 1. You could have carried the integration directly. You know, so I wrote it as 1 here, as 1 minus the integral from 0 to 2 of e to the minus x. And on the bottom as one minus the integral from 0 to 1 e to the minus x. But you could have just directly wrote on the numerator integral from 2 to infinity. That would have been the same thing. But here is what you get then. You get e to the minus 2, which I think 2 or 3 people got the solution. That is the probability unconditionally it takes longer than 2 months divided by the probability that it takes longer than 1 month. And then the answer is e to the minus 1. Okay, so it's roughly e to the minus 1, which is the same as the probability it takes unconditionally longer than 1 month to grade. There is no memory, you understand? It's a memoryless random variable. So whatever happened once this time occurred, it does not influence your probability of getting the success. Okay, so this is rather strange. Imagine what it would mean if if it applied to the lifespan of people. So for example, if you ask what's the probability a person that's 100 years old that the person would live another 100 years, and that probability would have been the same as the probability that a newborn lives another 100 years. Isn't it interesting? You understand? So it's a weird type of thing. For most events that you imagine, you think that that there is going to be some influence based on the time that passed. If you have waited for a long time to achieve something, to get the success, then it should take you usually less time to finally get to it. But not when that's a uniform, not when it's exponential random variable. It has what you call memoryless property, and that means the following. A continuous distribution is said to have memoryless property if, let's say, the probability that x is bigger than s plus t, given that x is already bigger than s, is equal to the probability that x is bigger than t. Okay, so that means, let's say you waited for something to happen, like for me to return the exam, already s units of time. And then what's the probability you have to wait additional t units of time? That's like the probability that you wait in total s plus t units of time, given that you waited s units of time. And that probability is the same as simply that x is bigger than or equal to t. Okay, do you understand the definition of memoryless properties? Isabella, you appeared. Very nice to see you. Yes? Do you understand how strange it is? Do you feel strange, guys? Or I don't know, right? You want me to what? To have a meltdown? I don't see you. I don't know if you feel strange or not. Show me your faces so I can know if you feel strange or not. Quoth the raven, nevermore. All right, so let's just verify. Thank you, Eli. But guys, yes, so another person I see. Good, good. It's truly weird not to, usually when you talk to people, you have, let's say, you see their faces, right, and you hear at least something, right? So it's a complete silence, especially through those earphones. Of the 100 years, well, but you recommend, Ugo, you recommend that I read this 100 Years of Loneliness about me, right? So that's exactly what happens here, right? Imagine if things are exponentially distributed, that would mean that, you see, whatever happened, it's like you started. I do feel this way truly. You see, look at it, right? So in the media and whatnot, usually when somebody very young dies, they say, well, what a tragedy. But when somebody dies and the person is 110, they say, my God, he's so lucky, right? So that's because they don't appreciate the exponential random variable. You see, to the person that lived 100 years, you know, it's as if life has just started now. Everything that happened before, it doesn't matter. So its probabilities are now reset, okay? It's now on the same, yes, 100 Years of Solitude. Apparently a very good book, and apparently about Arkady. So I have to read it soon. So you see, but what would happen is that if lifespan of people happen to be you happen to be exponentially distributed, then if you made it to 100 years, your likelihood to live another 100 years or whatever number of years is the same as somebody that was just born, right? Do you think that would have been fair? I think yes, it would be fair, right? Because whatever happened in the past completely erased. It's like every day is a new page. So here, let's just verify that the exponential random variable does indeed have this property, right? So you can just carry out. If I have variable with parameter lambda, so this is the exponential random variable with parameter lambda. You can just calculate, and you see that it indeed has the memoryless property, right? Just calculate probability that x is bigger than s plus t, given that it's bigger than s. Carry out the calculation, and you get that it's the probability that x is bigger than t. So in other words, whatever happened before, how much you survived before, how much you waited until something that, you know, for something to occur, the fact that you waited, it's completely erased, completely forgotten. And what is true is that the converse, right, is then true. The exponential random variable is the only random variable that has this property, okay? For continuous random variables, there is no other variable here, okay? Naturally, lifespan of humans cannot be modeled this way. It doesn't work this way, right? If you know a person is 110, you give probability of 0 that the person will live another 100 years, okay? So it's not exponentially distributed. So it's pretty weird. So this is the theorem. It says that if a positive continuous random variable with has the memoryless property, then it has to be exponential. It has to have exponential distribution. And we do this as follows, right? So notice this is called survival rate, by the way, right? So probability, why you call it survival rate is the probability that you will outlive a particular value, okay? So this survival rate is g of x, which is 1 minus f of x, which is it's 1 minus the cumulative distribution. So it's the survival distribution. It's the probability that you get a value bigger than x rather than below it, right? So then if you translate the memoryless property, then you see it's just the survival distribution for s plus t divided by the survival distribution at s. And if you have the memoryless property, that ratio happens to equal to g of t. In other words, it's as if you don't remember that you survived s, right? That's just the same calculation. Which means what? Which means that g of s plus t equals to g of s times g of t. And when sum is translated or converted to a product, you right away think exponential, okay? And definitely if you studied analysis or calculus, you think exponential. And here it is, right? So let's verify it's indeed exponential. So let's calculate what is the survival rate of n. In other words, let's say what's the probability you live more than n years. So I can break it apart, you know, and use this property. So it's gn minus 1 plus 1 until I pretty much get to 1. In other words, I can write g of n as 1 plus 1 plus 1 plus 1, right? And then I use this property recursively until I get g of 1 times g of 1 times g of 1 n times, or g of 1 to the power of n, okay? So it's the survival rate of surviving 1 year to the power of n is the probability of surviving n years. if you of course have exponential distribution. Sorry, if you have memoryless distribution, we don't know yet what it is, right? And similarly, I can figure out what is g of 1. G of 1 is g of 1 over n plus 1 over n plus 1 over n, well, n times. So based on that property, this property here, it's g of 1 over n to the power of n. And then upon taking n fruits, I see that g of 1 over n is the n fruit of 1, of g of 1. You with me, guys? Right, so what I'm saying is just that those are functional properties. That's how you can establish the exponential function all the same. So in general, I want to know what happens to a fraction, m over n. So g m over n is just like 1 over n added to itself m times. So that's g of 1 over n to the power of m, which is the same as g of 1 to the power of 1 over n to the power of m, which is the same as g of 1 to the power of m divided by n. Now, you see that, so what we have is that it's a continuous function, this g. So once I know what a continuous function does to every rational number, it determines completely what the function will do to any number x. So that means g of x must be g of 1 to the x. So if you studied analysis, you might be taking analysis, not with me a lot, but you might take analysis over the summer. By the way, if you need help with the subject, maybe I'll try to help with it, right? So I particularly like teaching this class. Even if you don't have a class, we can talk about it. I have notes and videos and whatnot, right? So g of x equals to g1 to the power of x. And this is just an exponential function. Do you agree? Some number raised to x is an exponential function, and every exponential function can be converted to have base e. Right? You do that by saying g of x equals to e logarithm of that g of 1, and you can drop the x, so you have this, right? And then g of 1, because it's probability, this number is less than 1, right? Survival rate is still less than 1 or equal to 1. So logarithm is negative, so I can define minus lambda to be minus ln of 1 over g of 1. Again, logarithms, this is the same expression here. I just write it so that now it's positive, right? So this number is now positive. Ln of 1 over g of 1, it's ln of a number bigger than 1, so this part is positive, and so I now have minus lambda defined as this power. This is minus lambda, okay? So then I simply now see that I have g of x is e to the minus lambda x. Yeah? And when I take the derivative, you can already kind of see it from the derivative, or or just convert first to the cumulative distribution and then take the derivative. You see that the density is that of the exponential random variable. So that was just a proof that x has to be exponentially distributed, pretty much, right? So for continuous random variables, that's the only type that will have it. And of course, I'm not sure if you would find, since I don't see your face, but you see, again, very hard to conceive or understand how anything in nature might have, might be memoryless, right? And right away when I wrote this, I thought, well, Alexander Gradinsky, he sings nothing on earth passes without a trace, and bygone youth is nonetheless immortal, right? Just to be sure that you know how that might sound, let me try to play it for you. At least 30 seconds of it or something. Let me know if you can hear it.
You can hear it.
No, I can't hear it.
Yeah, I think you have to share audio, maybe. We can't hear it.
You can hear it? All right, let's see. You don't. It should be shared. Let's see what is not shared here. Well, if you haven't heard, it's okay. I can send it to you. It's not a big deal. You gave up because of the comment? You know, too bad. You see, I should have let you be disappointed on your own, right? They have a very good beginning. It was interesting. I thought maybe like 3 comrades or something, but yeah. But yeah, I will send you this file. I'm not sure it's in Russian. I'm not sure how much you know, something that you don't understand can affect you. But immediately when I think of exponential random variable, I think of this song. Right? I just wrote it. It's that's why it's always sad. In the next example that I will give you once we meet again. True example, by the way, right? It's about my friend, and he's very tardy, right? If he says he will come, let's say at a particular time, I can be pretty sure that he would either come or not. You could wait for him infinitely long, right? So there would be a question regarding that. What else? All right, so just to emphasize what truly has what seems to have memoryless property, it seems that radioactive decay, right? Radioactive decay has a memoryless property. So success in this case is, let's say, for a particular particle, and maybe Jeremy can correct me, right? He knows better than me. Beyond mechanics, I know nothing, right? So you have a particular particle, and it will wait for some time, and then suddenly, boom, decays, right? So the time it decides to decay is like my friend, right? He decides to, like when my friend decides to come, just pretty much anywhere and anytime. And the fact that you waited, let's say, 100 years and the particle did not decay, it's equally likely to wait another 100 years, as if nothing happened, right? If you wait 1,000,000 years or 1,000,000,000,000 years, if the particle did not decay by then, its likelihood of survival further is the same as if it was just created, right? And then there will be other things, right? So the exponential distribution has connections with, let's say, Poisson distributions, and it's used as part. So understanding exponential distribution was just part in generalizing it to other distributions where they are not memoryless, but they are still in some part based on this distribution, and they're useful. Okay, so that's pretty much it for today. There would be this other problem. I just haven't finished writing it. I'll write it and I'll scan it, I think, after we're done. And you can try to think about this problem, which we will discuss later. So one person heard the song, but everybody else did not. Am I correct? That's strange. Well, I'll send you the song if you want. I'll tell you what I played, and if you like, you can listen to the entire thing. Okay. So. Well, good luck. Have a good one. Take care. Thank you for showing up. I hope to see you. I truly hope to see you, actually, right? With my eyes. Bye.
Thank you.
Take care.